All right. So welcome to this talk, which is going to be new features in SystemModeler 4, which is the about to be released version soon. And this talk is going to focus on the Mathematica part. So what you can do in SystemModeler, but from Mathematica. So this is an overview of the content of the talk. So I'm going to start with an introduction to what SystemModeler Link, this Mathematica package, is, what it does currently. Then I'm going to go through a whole bunch of integration and workflow improvements that will come in the next version. And then I'm going to go over to the big new features, which is model creation for Mathematica, structural model creation, and finally real-time simulation. And we'll start with the introduction to what SystemModeler Link is. So the short name for this is WSM Link. It's a Mathematica package for controlling and interacting with SystemModeler from Mathematica. So it's a package shipped with SystemModeler, so it gets installed when you install SystemModeler. It can basically be summed up in 3 categories of functionality. You can simulate SystemModeler models from Mathematica, get the results back in Mathematica format, interpolating functions. You can visualize things, either using special plot functions that come in this package, or just by using the data from the simulation and plugging it into the rich visualization features that are available in Mathematica. And finally, you can use it to analyze either simulation results or models directly through equations, or you can linearize your models and design controllers for them. For example, it's just a short list of examples what you could do. So then on to what's new in 4 in this package. So this is, as I said, a whole list of many small things that have been improved in the next version. So WM Simulate, you maybe saw it in Jan's talk before. It's a simulation function from Mathematica. Earlier you had to specify a full time specification from 0 to 4, which got kind of tedious. Now it just takes all those things, simulation time, what solver settings to use, if you set a step length or so in your simulation, it's all saved in the model, and Mathematica just picks it up. Or if you want to override it, you can of course do that with options, or say I want to simulate this model from 0 to 5. You can just give a number. Another small improvement, which is very small but will save lots of time, is that instead of giving the whole path to your model, earlier we saw, for example, if you wanted to simulate this Mathematica examples.simulation.Newton Cradle, which is a whole hierarchy path, you can just give Newton Cradle if that name is unique in SystemModeler, and it will automatically find that and simulate that. So it will probably save on lots of typing. You can use the WSM model data function to check if this lookup you're trying is going to work and what it's going to result in. And if it finds more than one match, it will give you a message about which matches it found, and so you can choose one of those. Another change is how models are represented in Mathematica. So again, the WSM model data function, but this time just of a class name or a model name, will return this what looks like a diagram of the model, but it's actually a little more than that. If I click on it, you see it has a blue border. It is an object representing the model, and I can do various things with it. I can right-click it, and it has a menu. You can click Simulate Model, for example, and it will automatically do this WSM Simulate. Or I can just do, as you can do with some other objects in Mathematica, such as graphs, you can just copy it. I just marked it and pressed Ctrl-C. And then you can do WSM Simulate and just insert it, Ctrl-V, and it works just like that. So you can use this object in place anywhere where you would use your model name. Another small workflow improvement is if you just want to quickly simulate your model and plot, look what one or two variables had value, and you're not interested in, at this moment, not interested in doing deeper analysis, just want to plot something quickly. There is now a shortcut, the plot function, which you earlier had to do first WSM simulate, get the result, plug it into WSM plot, and give the variables you want to plot. You can just give the model name to the plot function, and it will run the simulation, pick out the results, and return the plot directly. Right. Then there's some integration with new features in Mathematica, namely plot legends. So if you do WSM simulate of a model and then plug it into WSM plot, you automatically get plot legends with the variable names. And you can, of course, also customize these by using your plot legend option and specify any valid plot legend. And then you can refer to the expressions string to get the variable names, or you can use descriptions here and get the descriptions of those variable names in the model. Another feature which is available in Mathematica is dynamic diagrams. So for these diagrams you've seen in models, they are made up of graphic primitives, such as the graphics language in Mathematica, but a different graphics language. For those graphic primitives, you can also specify dynamic versions, which means that you can use results from a simulation, refer to variable names, and change the behavior, how they look, depending on those values. So here I'm simulating a tank system. I'm picking out the diagram for a symbolic time point, and then I'm animating that diagram from 0 to 250 with a certain animation rate. And you see that the tank levels are changing, hopefully. They should be changing. Okay, let's try that again. So what you would have seen is the tank level changing and some indications on the controllers moving up and down in the diagram, and that's all specified in the model editor or model center of SystemModeler. You can specify all those things, and they depend on the results from a simulation. So let's move on to the next thing, which is improved equation support. So in SystemModeler 3, we had some support for getting equations from a model into Mathematica, but it was limited. Some advanced SystemModeler model features were not supported. It's still not 100%, but it's better. Most notably, we now support translation of events and hybrid systems into Mathematica. So let's see if we can get back on track here. So here I'm getting the system equations for a bouncing ball model. Here you see the Mathematica text, which is basically the list of equations. And what's interesting here is this when statement in Mathematica, which specify that when the height goes below 0, then you reverse the velocity, so it's a bouncing ball. And you see that gets translated into the Mathematica symbol when event, which is how NDSolve handles these things. And one benefit of that is that we now can give method NDSolve to WSM simulate, which means that it uses NDSolve as a solver for these models. So if we run that, and then we get a WSM simulation data object back, just as if we had used a SystemModeler solver, and we can use it in WSM plot just the same way as we would have otherwise. There are some benefits for that, some applications. Let's see. There we go. So, of course, it's always good to have more solvers. Different solvers are good for different things. One thing where NDSolve behaves in a good way here is in some systems you will get a performance improvement if you want to run very many simulations after each other, because it does it all in Mathematica. There is no communication between processes and such. So if I'm just running this bouncing ball simulation for a bunch of different parameter values, it's going to take a while. And if I run that with ndsolve afterwards, we will see the timing differences. So it took 18 seconds for the WSM version, 2 seconds for ndsolve because it didn't have to communicate and between processes, basically. And if we plot the results, we see that they are the same. And ndsolve can also solve some complicated systems with its symbolic processing that WSM might have problems with. All right, so let's get into model creation. So this image kind of illustrates what we want to do. We want to have a bunch of equations. We want to say how those equations are connected, and we want to get a system modeler model. And then, of course, simulation results over here. So you might have many different sources for your models. And this is a list of such sources. You can either have some control models in Mathematica, like state space model or transfer function model. You might have equations. You might want to use a partial list of equations and extend something that's already available in Modelica. Or you might want to connect Modelica components together, such as, well, the equivalent of the drag and drop in Model Center, but you want to do it from Mathematica for some reason, because you want to automate something or try out different configurations programmatically. So now I'm going to show examples of all of that. So here we are creating models, mass spring damper and mass spring damper 2, with WSM create model. It's just the name of the model we want to have, and then you give in the object. This is the state space model, and this is the transfer function model. So if we go ahead and evaluate those, and then we can simulate them with a unit step and different parameters for the mass. It does that in parallel, and we can plot the results. And well, that's the response. And you can also model based on equations. So here we have a 2-tank system, and we also have a leak that's not illustrated in the second tank here. This is constructing a list of equations and a list of initial conditions. We have a list of parameters, and we can use WSM create model again, but this time with a list of equations, an independent variable, and a list of parameter values. And if we do that, we can just use WSM simulate to simulate the model we just created. And we can use WSM plot to plot the result. So this is one example of how you can create Modelica models without actually writing Modelica code.
Can you show the result in Mathematica?
Sorry?
You create them in Mathematica?
Yeah. That's what I'm doing. This is the list of equations, and WSM create model translates that list of equations into a Modelica model.
Can you show the corresponding result?
Yeah, I can show the corresponding. So if I switch to Model Center, you see it shows up under user classes. And if I look under the text view, it's translated into a nice list of parameters, variables it uses, initial equations, and equations. And it has even translated these special characters into Modelica compliant ones. All right. This also has support for when event, which is, again, the ndsolve version of specifying events. So here I have a list of equations, very simple. The velocity is the derivative of the height. The derivative of the velocity is minus 9.81 gravity. And when the height goes below 0, we reverse the direction. And finally, an initial value for the height. If we create that model with WSM create model, we have a bouncing ball model. We can just simulate it, and we can get a plot. What you also can do is extend models that already exist in libraries in SystemModeler. For example, here I'm going to extend translational mechanics component. So this basically specifies an interface, what connectors should it have, and a bunch of variables we can use. So here the variables are the relative distance between the connectors and the force acting between them. And what I then just have to do is add the equations that are missing, basically specifying the force and the relation between the velocity and the position. And I can do that by using the element notation for WSM create model. So I'm creating a unidamper model, extending the partial model here, which I define up here. So this is an already available Mathematica class, and I'm adding my equations to it. And I'm going to show how we can use this model I just created very soon. And that brings us to structural model creation. So this is the equivalent of drag and dropping things in Model Center, but doing it from Mathematica instead in a programmatic way. So the information you need for an operation like that is what components do you want to use, what type do they have, and how are they connected. So first a list of components with name and what type they are. And here you see I'm using the short naming. There is no real input on top level. It's far down in the library somewhere. But there is only one, so I can use real input. I'm giving them names. And finally, I'm giving a list of connections. And here I'm using the undirected edge notation from the graphs part of Mathematica. You can also use rule or directed edge. It works just the same. So what I'm doing here is connecting the connectors of these components indicated by the dot notation. So here I'm connecting the flange A connector of the damper with the flange B connector of the mass. So here you might need to know a little bit Mathematica, at least to understand the connector concept and how they work. So basically, this is the part with the connection lines you draw in Model Center. And finally, I'm giving all this information to WSM Connect components. Giving the model I want to create a name. And then I didn't have my damper in this list of components here before. I'm adding that because I want to create two different models, one with a damper and one with the unidirectional damper we created on the slide earlier. So I'm creating that with the list of components and list of connections. And once that's done evaluating, you will get this system, which is, well, a system completely in Mathematica with the diagram, different components. And you see this spiky here is the component for the unidamper we created on the slide earlier from Mathematica. They get it, all the models created from Mathematica get a default icon, so you recognize them. You can change it to something more appropriate later. And I'm also creating the same system, but instead of the unidamper, I'm using a normal damper from the mechanics library. And once that is done, I'm going to push on this force here. So I'm going to push the mass with the unit step. So I'm going to push it and then simulate the model and see how the mass moves over time. So I'm defining a step function using WSM simulate of the two models we just created. And also setting a damper value. And I'm doing this for both the unidirectional damper and the normal damper system. All right. And finally, I'm doing it with the normal damper system, but I'm setting a damper parameter of 0 so we can compare it what happens if I don't have any damping at all. So I'm simulating that as well. So now I have 3 simulations. And I'm specifying some plot legends. And finally, I'm plotting the mass position over time from these 3 simulations. So the yellow line here is the no damping, which means it just goes back and forth, which makes sense. It's just periodical back and forth. If we look at the pink one here, it's the one that damps in both directions. So it's quickly damped down to a basically constant value. And if we look at the blue one, we see that it follows the undamped one in one direction, and then it gets damped in the other direction. So the unidirectional damper is working as intended. All right. And then on to the last topic, which is real-time simulation. So earlier you could do this in Simulation Center, but now you can do it from Mathematica, which adds a bunch of possibilities. So for this we have a couple new functions. We have WSM real-time simulate. I'm going to use this Newton cradle example again. I've used it before. So I'm going to simulate it for 200 seconds. So I'm starting that simulation up, but I'm not actually starting it. I'm just launching it. Because I also want to do a WSM real-time plot. So this is going to give me a real-time plot of these variables. And you see I used the connection reference I got back from real-time simulate. And I'm going to do the latest 4 seconds of that simulation I'm going to show in this real-time plot. So if I start the simulation by pressing the play button, you see the last 4 seconds of it. And that's just one way to get data out from a simulation. You can also use the simulation connection object and give a variable name, for example, x1, and when you evaluate it, you get the current value of that in the simulation. And that, of course, enables you to use dynamic and refresh to actually show them live. Or you can use them in any visualization you might want to use, such as gauge. And there's also more advanced functionality for retrieving data from a simulation. Basically, you can give it a function to call every time you get a new data point, which I'm not showing here. So let's stop that. Let's remove some output. All right. And let's actually control the simulation. So for that, I'm going to use Simulation Center because we're going to use a feature there that's not available in Mathematica yet. So it's building an inverted pendulum, and I'm going to run it in real time. And I'm going to start it up, pause it, and then I'm going to check which port it actually started on. And I'm going to connect to it with WSM Real-Time Connect. And what you get back is a connection object very similar to the one you get when you start one from Mathematica Real-Time Simulate. And I want to control this with a slider. So I'm making a slider controlling the variable x, setting the ref variable in this simulation with x. And I'm giving it as a function, which means it will be called every time you communicate with this simulation. It will set ref to the value of x. And now we want to show the animation for this simulation. And now I will see if I can have both of these on screen at the same time. That will be a challenge with this resolution. So what I actually want to show is the slider down here. Okay, let's see. When we start the simulation back up, zoom out a little. And you see it's all the way to the left because my slider is all the way to the left. And if I move the slider a little, so I slide the slider to the right, and the simulation responds in real time. And you can control the reference signal for this inverted pendulum from Mathematica. And this model actually has a really good controller because how fast you can't really push it. So that enables you to control simulations from Mathematica in real time. And there's a bunch of applications for this. So this interface has very general possibilities. You can execute any Mathematica function for new data points. That could include fetching stuff from external devices or, well, anything you might want to do. You can also execute any Mathematica functions to set new input values. And you can change parameters in the model live while the simulation is running. And you can use this for a bunch of different things, such as you could use current and historic simulation data you collected from the simulation to decide what input values and parameters you want to set. For example, you could implement a real-time controller in Mathematica for an external simulation. Or you can use Mathematica's input functionality, so a gamepad or something to control the simulation. Or you could construct a dashboard for monitoring such a real-time simulation. So there's lots of possibilities in this interface. So this is a summary of the features I've talked about. Lots of small improvements to workflow, which will hopefully save lots of time and everyday use of SystemModeler. Improved integration with new Mathematica features and solvers. You can now create models from Mathematica. And there is real-time simulation and control from Mathematica. And as Jan mentioned, there are more talks coming. And thank you for listening.